In this demo, we'll demonstrate to you how our application, the digital stethoscope, will look like and its function. This application aims to help users diagnose heart sounds with an easy-to-use interface. Let us begin by launching the app. When the app launches up, you can see there is already pre-existing recorded sound files in the table view. To record a new sound file, just click the plus sign here and press the red dot button. To finish recording, just tap the screen once. Over here, the users have the option to rename, change the date, playback, and the option to save the sound file. Now, to run a diagnosis of the heart sound, we first select the targeted sound file, and we can just click the Compare Heartbeat button. We can choose to switch on the filter or let it remain off. The filter will act to block out sounds from 500 Hz onwards. When the Compare Heartbeat button is pressed, the user will be redirected to the screen where the users can choose from 4 common measurement areas where heart escalation is normally performed. This screen shows the analysis of the heart sound. The waveform is of the recorded heart sound. There is an option to scroll and magnify the waveform for a better view. The users can click the Detail button for more information on the diagnosis. The users will then be redirected to a new screen where the users can perform further analysis. There is a view on both of the heart sound where the first is the recorded heart sound of the waveform and the second is the waveform of a particular heart disease. The user can easily compare both the waveform to see the accuracy of the diagnosis. There is also a brief description of the diagnosis alongside with the symptom usually present in patients with this diagnosis. For more information about the heart disease, the user can opt to go online by clicking the Go Online button, where they can choose to view either Google search result or information about this diagnosis on Medline or Mayo Clinics. These two websites are two established hospitals with large research database in the USA. At any time of the analysis, the users can opt to return to the area of measurement to reanalyze or select a new area of measurement. Now, please let us give you a brief presentation on the technical side of the mobile application.
So, for the rest of the content in our presentation, we will be going through the hardware of the project, then looking at the UI interface layout, then detailing through the digital signal processing techniques that we used, going through our database, then the analysis of our mobile app, some feature improvements that we could have made, and then our conclusion. For our project aim, there are a multitude of digital stethoscopes available on the market. However, their dedicated hardware and software make them very costly. So, by utilizing an iPhone's quick processor and ability to access information from the internet, while also having a built-in DAC and ADC, this project aims to provide an inexpensive alternative to save and record heartbeats, while using signal processing techniques to output heartbeat information from heart rate to heart disease symptoms. So, the target audience for our digital stethoscope project is aimed towards medical practitioners who may want to use the product as a second opinion to validate their diagnosis. Our project is also open source and available to the public. This is especially useful as it becomes a learning tool for medical students.
Hi, I'm Stephanie and I'll be talking about the hardware of the project and the user interface layout of our application. Let us begin with the hardware of the project. The hardware is only used to record heart sounds for analyzation of the mobile app. There are 4 main components used in creating the hardware. The first component is an acoustic stethoscope head sourced from an inexpensive stethoscope purchased from Sutherland Medical. The second component is a rubber tubing from the same stethoscope that is cut down to an appropriate length to allow proper transmission of sound from the stethoscope head to the microphone. The most important part of our hardware would be an iOS-compatible microphone with a 4-pole TRRS connector used to allow sound input. And lastly, we have a 3D printed holder designed by us to store the wire of the microphone and connect the medical tubing to the microphone. Unfortunately, upon further testing, the sound from the stethoscope is found to be too soft and the S2 hard sound can't be heard. As the stethoscope was not an essential part of the project, we have decided to not replace the stethoscope due to funding constraints. Next, I'll be talking about the user interface layout of our application. Upon launching the app, the users will be presented with a recording menu where users can record or playback a sound file. The sound files are saved and managed with Core Data, a framework from Apple which allows data management using Stack. The recording function was also accomplished with Apple's own object class, AV Audio Recorder. The data is then passed to Signal Processing Controller. In this controller, waveforms of the recorded audio is displayed with implementation by an open source library, FD Waveform. When more information is selected, the embedded web page is accomplished with Apple's API, which is the Application Programming Interface, UI View Web. All the data are passed around the controllers using manually created segue. Segue in iOS is used to define the flow of the app's interface. Now I'll pass it on to Chris to talk more about the signal processing function.
For the pre-processing part, originally the input signal would be sampled at a common sampling rate of 44.1 kHz with 2 channels and at 16-bit PCM format. However, this would make the input file size unnecessarily large. So, to reduce the amount of information that we work with and receive, we sample only one channel at 5512 Hz. We can remove one channel because the microphone we are using is monophonic and can only capture one channel. That would mean that the other channel would be a replica and would be redundant. So, the input size was reduced by half just by removing this one channel. Also, sampling at 5512 Hz will capture 1/8 of the data than 44.1 kHz. So effectively, we reduce the data again by a factor of 8. So in total, the amount of data that we work with is 16 times less than if we chose to use the original input signal. This will make file processing faster on the iOS devices processors as well, as there is significantly less information to work with. Through frequency analysis, we found out that the frequency components of a heartbeat is between 0 to 500 Hz. The reason why we didn't sample at 500 Hz is because we won't be able to replicate the original signal at that sampling rate, whilst it also introduced aliasing. So we will have to sample in accordance to the Nyquist range, which states that a signal can be accurately reconstructed if sampled at twice the bandwidth of the original signal. However, 1 kHz sampling rate for our application would still not be enough, and at this sampling rate, the signal would still be subjected to phase distortion and a loss of resolution. Now, most modern analog to digital converters have built-in analog anti-aliasing filters. However, we still use a process known as oversampling to overcome the effects of the heartbeat information being aliased. This is why we are oversampling at 5512 Hz. On top of overcoming aliasing, it also averages out noise for better signal-to-noise ratio than if we sampled at 1 kHz. After this collection process, we then amplified the PCM values by a factor of 4. This makes the S1 and S2 characteristics of the heartbeat more prominent. However, noise will also be amplified, but we pass it through a low-pass filter with a cutoff frequency of 500 Hz in order to reduce the amount of background noise.
The project we designed uses an audio fingerprinting algorithm to compare and record heartbeats to a database of heartbeats with murmurs. The main steps in this algorithm that will be explored in this video are the sliding FFT, the spectrogram creation, the wavelet transform, fingerprint creation, and fingerprint comparison. To create a spectrogram, we take multiple fast Fourier transforms in an overlapping sliding fashion along the recorded signal. Each FFT contains the frequency spectrum of the recording for the given duration of the window. The frequency content gives us important information on the signal and characterizes the specific sounds in each murmur. A large window will provide better frequency resolution but worse time localization. We chose a window size of 2048 samples. A smaller space in between each window will offer more overlap and creates finer detail in the spectrogram view, at a cost of increased processing time due to more frames needed. An example is shown at the bottom of the page, showing the overlapping windows and how we apply the Fourier transform to the recorded signal. The result of each FFT frame is placed into a two-dimensional matrix. Each row contains the frequency content of each frame. The descending row represents each step in time. This is visualized in the image below on the right. The resulting matrix can be heat plotted to represent a traditional spectrogram, with the horizontal axis representing time and the vertical the frequency spectrum. The color of the plot shows the magnitude of this frequency content. This can be seen below in the plot on the left. Given the parameters we chose when performing our sliding FFT, our spectrogram has a frequency resolution of 2.69 Hz and a time step of 11.6 milliseconds. Our reasons for these parameters is discussed in the report. The spectrogram matrix is broken down into smaller spectral images, containing a simplified representation of the frequency content with a granularity of 1.48 seconds. These images contain the data used to create a sub-fingerprint. To aid with data extraction, we perform a Haar wavelet transform to extract the approximation and detail coefficients. These represent the big picture and the finer details, so to speak. An example of the Haar wavelet transform can be seen below. The red shows the approximation and the blue shows the detail. The transform process is described in our report. From our wavelet matrix, we extract the 200 largest magnitude wavelets as these best represent the data. We create a sub-fingerprint by forming a Boolean array filled with zeros. The 200 extracted wavelets are sign encoded to fit into the array. Positive wavelets are represented by the code 1, 0. Negative wavelets are represented by 0, 1. The sign encoded wavelets give a sufficient representation of the audio contained in the sub-fingerprint. The sub-fingerprints form a 2D array, with each row representing the signature of 1.48 seconds of audio. To wrap up the fingerprinting process, we can compare fingerprints of different audio by comparing the content of each sub-fingerprint. Due to different recording lengths, the size of fingerprints may vary. To account for this, the smaller fingerprint is slided over the larger one, and the match quality is compared at each slide position. This can be seen in the figure below. The whole process outputs the maximum percentage match that occurs when comparing fingerprint content. This wraps up the fingerprinting process. Here we have the results of the fingerprinting process, showing the accuracy of the algorithm under a few tests. 70% is regarded as a pass. The project can successfully detect heart murmurs with added noise and differing tempos. The algorithm struggles when recordings are out of phase. The algorithm also successfully differentiates between different murmurs, as can be seen in the last graph element. The process is also fast, only taking a couple seconds to compare multiple murmurs.
In our database, we have used heart sounds from the aortic, pulmonic, and mitral area of the heart. The reason to have different heart sounds at different areas is because the S1 characteristic of a heartbeat may be more prominent than the S2 characteristic, and vice versa. And so that's why we collect at various heartbeats at various locations. We get these heartbeat sounds from the Michigan Heart Sound and Murmur Library, which can be found online, which has a brief description of any heart issues from its associated heart murmur. Originally we wanted to collect data ourselves, but due to the Privacy Act 1988, there's a long application time as collecting health information would need the individual's consent, and so we could not just go to a hospital and ask to use heartbeat database for our project. The Human Research Ethics Committee must also approve of us using health information for research purposes, and if that lengthy process is granted, it would also be unethical for us to release our open source project to the public as people will have access to private health information without the owner's consent.